Assalamu alaikum warahmatullahi wabarakatuh. Rabbi shrah li sadri wa yassir li amri wahlul uqdatam min lisani yafqahu qawli. Rabbi yassir wa la tu'assir wa tammim bil khair. In today's video, we will continue our topic of induction motor. But in today's video, especially, we will going to look at the single phase induction motor. Before understanding about the single phase induction motor, that as we know that electricity was when for first electricity was produced as AC single phase in 1880s and early 1890s. So that was at 133 hertz single phase. So with the materials and techniques at that time available, it was not possible to build an induction motor that could properly work. So the induction motor was not very popular until the three-phase 25 hertz power system was developed in mid 1890s. So as we have seen in the three-phase induction motor, we have the inherent property of rotating magnetic field in the three-phase induction motor. So that's why that was popular at that time, and then it was different techniques were developed to produce the single-phase induction motor. To basically understand why single phase induction motors have the problem, because they cannot produce the rotating torque by itself, that could be understood by using these two theories. One is the double revolving field theory, and the other one is cross field theory. The double revolving field theory actually explains about how if we just apply a single phase to a single phase supply to this single phase induction motor, so what will happen to the fields, and we will not have any torque produced in the motor that can be able to rotate the motor. While the cross field theory will tell us what will happen to the voltages and currents while once if it is rotated by any means, what will be the consequence if we have means by some means, if we just rotate the motor and near the synchronous speed or near the speed where it can rotate on the in the machine. So whatever is so we will have these two different theories, double revolving field theory and cross field theory. Let's look at them one by one. So the first double field revolving theory, it says that a stationary pulsating magnetic field can be resolved into two rotating magnetic fields. Now just understand what happens if we just have a single induction motor, a single phase induction motor, and we just apply a single phase supply. So as we know that it's not rotating at all, and it will induce a voltage in the rotor. Obviously that is also not rotating, so that will keep it locked in locked position, and that will be just like a transformer with the secondary short circuited, because the squirrel cage rotor of the induction motor, as we have earlier known, that it is shorted with the short rings at the end of the bars of the rotor. So there will be huge currents that will be flowing into the rotor, but there will be no torque produced in the motor that can be able to rotate it. So let's look at what happens to the magnetic field inside once we apply the single phase supply to this single phase induction motor. So when we apply this, so that the induction motor, they will produce a stationary pulsating magnetic field, and that pulsating magnetic field, we can divide it into two rotating magnetic fields, and that will be equal in magnitude but in opposite direction. So the induction motor responds to each magnetic field separately, and the net torque in the machine will be the sum of the torques due to each of the two magnetic fields, and we will just name them as this forward rotating field and the backward rotating field. So the pulsating field due to various magnitudes of field at different time. So no rotating stator magnetic field. So a single phase induction motor has no starting torque. So we must be understood that it has no starting torque, and we have to do something to rotate it. But first we are looking at what happens to this, why this there is no starting torque in it. So the flux can be divided into this. Clockwise flux will be half B max cos omega t in the direction of iota, and minus 1 over 2 B max sin omega t in the direction of j. And similarly for counterclockwise flux, that will be just plus and minus B. So the total flux will be the sum of these two magnetic flux. So the sum of the clockwise and counterclockwise magnetic fields is equal to the stationary pulsating magnetic field. So this is the stationary field B max cos of omega t in the direction of I. So this is how we can look at these revolving field theory, which was also known as Andrew-Blondel quadrature field theory. So we will see the resolution of a single pulsating magnetic field into two magnetic fields. So in the starting, assuming that we have this Bs in this direction, and one of the field is rotating in counterclockwise, BCCW, and BC field is rotating in clockwise direction, and it will have some rotation here. So but at this point we will see they are at opposite 180-degree apart from each other, and then they are moving in the other direction, and they will clockwise is crossing each of them. So they will rotate in opposite directions, and at the end there will be no magnetic field, there will be no torque that will be induced in the motor, and we will not be able to rotate this motor. So basically the stator magnetic field, actually here we can see that it is being divided into two magnetic fields. One is rotating counterclockwise, and one is rotating in clockwise direction. And obviously they are approximately of the same size, and they are cancelling the effect of each other at every point. So there will be no net magnetic field that will be used to produce the torque in the motor. But the torque speed characteristics, here we can see we can see that there is no starting torque here. These dotted lines actually are used from the forward and backward magnetic fields. So the torque speed characteristics of a three-phase induction motor in response to its single rotating magnetic field is shown in figure. So that is we have just made them according to our knowledge of the three-phase induction motor torque speed characteristics. So a single phase induction motor responds to each of the two magnetic fields present within it. So the net induced torque in the motor is difference between the two torque speed curves. So at every point it is at the difference point. So we can see that it is in the forward direction, and it is in the backward motoring, or the forward motoring direction. So the most important point to understand here in this, that we can see that there is no starting torque in this motor. So this was the double revolving field theory. Now let's look at the cross field theory. It is different than the double revolving field theory. So cross field theory, this theory is concerned with the voltages and currents that a stationary rotor magnetic field can induce in the bars of the rotor when the rotor is moving. Now here remember this thing, that we are assuming that by some means the rotor is rotating. So voltages are induced in the rotor bar. So the voltages are now induced in the rotor bar. So when the peak voltage occurs in the winding directly under the stator winding, so due to high inductance and short circuit of the rotor bars, the high current lags 90-degree. So the rotor magnetic field is somewhat smaller, here we can see, than the stator magnetic field because of losses in rotor, and both magnetic fields differ by nearly 90%. Here we have assumed that it is 80% in both space and time. So what happens now, remember again I am repeating this, that now the rotor is rotating by some means, we have made it to rotate. Now if we just add these points at certain points, so we will get some net magnetic field at every point. So that net magnetic field that will be produced here in this single phase rotating motor when it is being rotated by some means, so it will be rotating in the counterclockwise direction. So, with the rotating magnetic field present in the motor, the induction motor will develop a net torque in the direction of motion, and the torque will keep the motor turning. Similarly, if the motor is turned in clockwise direction, the resulting torque will be clockwise and keep the rotor turning. So, to summarize this, what we have seen in this video is that we know that induction motor is not self-starting. It has no starting torque. So we have just seen what actually happens if we supply a single phase voltage to this single phase induction motor. So if it is in a stall position or it is not moving at all, so it will not move at all. It will, because it has no starting torque. So we have seen that the double revolving field theory, that the magnetic fields are divided into two parts and they are rotating in opposite direction. One is clockwise and the other is counterclockwise, and the net magnetic field will be not able to produce any torque in the rotor. Similarly, via the other field theory, cross field theory, we have seen that once if we make by some means, if we rotate the motor, so what happens that the it will start rotating in the direction, and it will keep on rotating in the direction of the motion that we have provided in the beginning of this in the beginning, to rotate this motor by some external means. It could be any prime mover or anything, or any other small motor, or whatever is the method we are using. But once it is being rotated, it will continue to rotate. I hope you have understood so far. So we will continue with this topic in our next video. Assalamu alaikum wa rahmatullahi wa barakatuh.